My name is Kelly Paffel. I'm Technical Manager for Invino Engineering, LLC, located in Tampa, Florida. Our firm is focused on steam and condensate systems. And today I want to talk about steam trap station testing methods. The two methods I want to talk about are the temperature method and the high frequency ultrasound method. One of the questions we ask is, why test steam trap stations? Number one is optimization. Proper end user performance. A steam trap blowing through on a heat exchanger or steam coil or a reactor jacket will reduce the heat transfer efficiency by 11%. The other thing is that we want to ensure 100% steam quality going to the end users. So without proper steam trap stations on our steam distribution system, we will not remove the condensate that can form in the steam line. Therefore, the condensate degrades our steam quality. The end user requires 100% steam quality, and it's up to us to maintain that steam quality. The next is system reliability. Eliminate component failure. Failed steam traps in the open position or even the closed position can cause severe water hammer, and it does all the time, which we can have major failures of steam or condensate lines in our system. The other thing is piping failures. Condensate that's not removed from our steam distribution system because of steam trap station issues will have entrainment into the vapor and can erode elbows and cause erosion. The next thing is reduce emissions. A steam trap blowing through will cost us tons of CO2, tons of NOx, and tons of SO2. For every 1 pound of steam that's blowing through a steam trap, that's 1 pound more steam I have to produce at the boiler, which is lost. Yes, finally save energy. But the question is, which has higher energy loss? 250 psi steam or 25 psi steam? Most of the time the answer is 25 psi steam, because the 25 psi low pressure systems discharge into a condensate tank that's vented to atmosphere. The 250 psi steam system should be going into cascade system. Therefore the thermal energy is not lost, only the mechanical energy. So the plant must decide where to focus their attention. Results from testing the steam trap station. Performance or lack of performance. Steam trap is isolated or not in operation. Priority number one, test result. It's a major safety issue. Go out all the time on steam distribution systems and they have their steam traps blocked out, isolated. These are critical steam traps. The steam traps are put there for a reason to remove condensate that will form in the steam distribution system. If the steam trap is not in operation, condensate can accumulate and cause severe water hammer. So these are always priority number one. Blowing steam or completely fail. Priority number two result. Yes, energy is an item, but more so, our condensate systems are not designed for steam traps blowing steam into the condensate return line. This steam going in there and trying to expand 1,600 times will increase the velocities in our condensate line above 4,500 feet per minute and cause, again, severe water hammer. So these are priority number two. Priority number three is leakage during steam during operation. The other ones are processes not in operation, and of course we want all of them to have proper operation. The question comes up, when or how often should the plant test the steam trap stations? Every 3 months until the failure rate during any steam trap station assessment is 3% or lower. Today, we should not have any steam trap survey or assessment to have a failure rate above 3%. After the failure rate is lowered to 3% every 6 months. Next is prioritize testing your steam trap stations. Number one, largest potential for creating issues. So if I have a reactor, I want proper drainage, that would consider to be a priority number one. Methods for testing steam trap stations: visual, temperature, ultrasound. People always ask me, what's the best method for testing steam traps? Using all three. Visual is very powerful. I walk in plants all the time and say, that steam trap is bad. And people say, you're just looking at it. How do you know it's bad? Because it's upside down. The other thing is I'll be talking about is temperature and ultrasound as the other two methods. Temperature measurement. The relationship between steam pressure and temperature. Extremely helpful in understanding many different operating conditions of the steam components. Number one, I come in and I'm going to do a steam trap station assessment. I want to know if the process is in operation. Next thing I want to know is the steam trap station in operation. The other thing I need to know is what the operating steam pressure is, because that's part of my calculations for energy loss, making sure I have the correct orifice in the steam trap for the correct pressure. The other thing is the condensate system pressure. So sizing a steam trap, you need to know P1, steam pressure inlet, and 2, condensate. P2 is condensate. So temperature gives me a lot of information. Infrared temperature measuring is very quick and a versatile tool. Requires training and ensure success. Like any tool that you use in the steam or condensate system, training is essential. So people totally understand how to use the instrument to its fullest capability. Diagnostic tools have positive features and negative. The thing is that we always want to know the positive, of course, but also we need to know the negatives. One of the negatives with temperature, we're taking the surface temperature. Corrosion, paint, and insulation all have a negative effect of us taking that temperature measurement with non-contact measurement, which is infrared. Temperature measurement, non-contact, important to understand the negative attributes to ensure an accurate temperature measurement, which I just talked about: clean surfaces, insulation, etc. Temperature measurement devices must be an integral part of your steam trap station testing program. So you must have all the tools when you go out to do a steam trap assessment. Temperature measurement. Estimate the steam pressure by using a temperature testing device inlet to the process. So up here at T1 up here, so we gain the knowledge of the steam going into the process. Also gain knowledge of the condensate pressures present in the system, down in here and here in the system. Estimate the condensate line pressures, which I already talked about. So temperature gives me a couple different, very critical pieces of information. The next is an example of using the temperature method. When I'm using a temperature method here, I take a measurement up here. It's 299 degrees Fahrenheit. The steam trap body down here should be close to the inlet. Yes, there's a slight pressure drop through the heat transfer, but we should be close. So when I go up and testing the process, steam trap operation, I want to take an inlet to the process, 299, and I want to test the steam trap body, 293, 285. Yeah, steam trap is working good. This is true for 96% of the steam process application. There are some process applications where we have a tremendous amount of pressure drop through it, and that would have an effect on the temperature at the steam trap. But 96% of the applications, we can use this method. Low temperature measurement at steam trap. When I come up to test the steam trap, One of the things I want to make sure is that if I'm up at 210 degrees, if the steam trap body is now up at 210 degrees or higher, then the steam trap is not in operation. Then I need to proceed into root cause analysis. Understand if undersized steam trap, is there fall strainer, is there high back pressure in the condensate line, etc. So I come up, the steam trap has to be 210 degrees or higher before I proceed to the high frequency ultrasonic test. Surface temperature can be very useful in evaluating various potential conditions. Using it alone for testing steam trap stations will have a low accuracy for testing steam trap performance. People always ask me, can I test steam traps by using temperature? It's very, very, very difficult. Different statements are made. I've heard them throughout my career, that if a high temperature differential across a steam trap station, the steam trap is good operational condition. There is no or very low temperature differential, then the steam trap is blowing through. These statements are not correct, and I'll kind of explain why I am saying that. Here's an example of a temperature measurement performance. So here I have 299 degrees here at the inlet to the steam trap, and at the outlet I have 214 degrees. So I have a high temperature differential across the steam trap, and by the statement high differential temperature across the steam trap is good. In essence, steam trap is blowing through. Why? Because down here the condensate line is running at 0 psig. As the steam passes through the steam trap here, the steam has to get its temperature down to 212 degrees. Now, yes, there'll be a small percentage of superheat generated by the pressure drop across the steam trap, but condensate passing through there will zap the superheat out of the steam and bring it close to saturated conditions, or I put down 214 degrees. But the steam trap is blowing through. The thing is that the dynamics of the system is always based down here on the condensate return line. So another example here is 299 degrees going in here, and I have 284 at the outlet of the steam trap, and there's no differential, which is the statement says if there's low differential across the steam trap is blowing through. Well, incorrect, because the condensate line's operating under pressure. So the steam coming through here, flash or blow through steam, is only going to come down to whatever pressure is in this condensate line. So the dynamics of the system really bases what we have for inlet and outlet pressures. So it's, again, very difficult to analyze steam trap performance using temperature. One more example, and this is a low pressure operating system. Let's say low pressure down here. Let's say 30 psi or something like that. I got 220 degrees F, 212, and I'm going into an atmospheric system. So there's low temperature differential. We don't know if the steam trap's blowing through or if it's good. And that's why we use high frequency ultrasound as our other test method. But again, never go out and do a steam trap station assessment without having temperature with you. Temperature measurement procedures, process inlet, we just talked about. Steam body temperature on the steam line drip leg traps must be 210 degrees or higher before proceeding into high frequency ultrasonic test. Representative temperature, you want to scan 6-10 inches up and down the pipe to get a reading, average reading of the temperature, because again it varies because of rust and paint and process fluid dropping in on the piping. So scan, just don't take one spot. And the other thing is that temperature measurement, always make sure you understand target area. A low-end infrared unit will have a very, very large target area, and the higher cost units will have a much lower target area. And the other thing is that Testing with temperature must be part of your SOP, and I'm big on SOPs, so your SOP for testing steam traps should be, I would say, at least 50 pages in length. It must be detailed to ensure accurate testing of steam trap stations. If you don't have an SOP, how do we know that people are testing the steam traps correctly? It's a big question. So I'm a big believer that everybody follow an SOP when they're doing steam trap station assessment. Next, I want to talk about steam trap ultrasonic comparison method. So one of the things using high frequency ultrasound, it's always been a question. We're going out and testing the steam trap. Where do I set the sensitivity? Well, if I set the sensitivity of a unit, then it's not volume, it's sensitivity. If I set the sensitivity too high, all the steam traps are going to test fail. Why? Because I can pick up a leak level 1 times 10 to the minus 3 with using high frequency ultrasound. All right, turn the sensitivity all the way down. It's too low. Then all the steam traps are going to test good. So, where do I set the sensitivity? There's people say, you set the sensitivity here for inverted buckets. You set it here for flowing thermostatics. That's all questionable. So you must do what we call the comparison method, because every steam trap is going to have some different dynamics to it. And the different dynamics, we have to set up what we call baseline information. Now, the comparison method was developed by an engineer out of Minneapolis, St. Paul, many years ago. It proved tremendously successful when we applied it on steam trap management programs and crossed it with root cause analysis. We found accuracy levels up above 98.5% accuracy using the comparison method. So the comparison method, basically what we're looking at is upstream, we call test point number 1, downstream, point number 2, and point number 3, downstream of the condensate discharge orifice in the steam trap. By setting up these benchmarks and adjusting the sensitivity, what we're doing is blocking out any competing ultrasound that might be occurring in the system. Therefore, we can go up and do an accurate test of the steam trap performance. So if I didn't have the benchmarks, I go up with one standard sensitivity setting, and then I could be picking some background or competing ultrasound up and throw my readings off. The method allows the steam trap station assessor to establish a base reading to filter out any competing ultrasound, which we just talked about. That can be generated upstream or even downstream. Without using a comparison method of testing, it's very difficult to assess the steam trap performance because the technician will not know where to set the sensitivity setting. Again, there can be competing ultrasound, and the comparison method is just getting, that competing ultrasound baseline out of our actual reading or testing of the steam trap performance. The ultrasonic unit must be at 25 kilohertz, and unfortunately, this says 40. We scratched that, and it should be 25. At 25 kilohertz, we found that gives us the highest clarity of a steam or condensate passing through the orifice of a steam trap. To activate the ultrasonic units, pull the trigger. If the instrument is within the sensitive range, the decibel dB indicator will blink. The decibel reading should be set to about 20 dB. So we want to go out and make sure that we're getting a reading up here, 20 dB or higher when we're testing the steam traps. The setup for testing the kilohertz frequency indicator must be steady and not blinking. One of the things I always find when I'm training people for the testing steam traps is they gotta be aware if this is blinking, it's in the mode to change the kilohertz, so you're not picking up any ultrasound. So you always have to be aware of that. So once the sensitivity mode is set for 25 kilohertz, it's set. Okay. The sensitivity dial, which is located right here, turning it clockwise increases the sensitivity, counterclockwise decreases the sensitivity, and simultaneous the level in the headphones. So, the other thing, the instrument needs to be in range for accuracy, so it gives us indication, there'll be a blinking arrow telling us to increase sensitivity, or they'll know there'll be an arrow telling us to decrease the sensitivity. So it's a very handy unit to have out in the field because it gives us a lot of information. Again, too high will give us a pointing area and just reduce the sensitivity to get back within range. Now, when I go out and test steam traps with high frequency ultrasound, there are two types of operation: on-off, continuous flow. And on-off, we're using high frequency ultrasound. Is this? So if I was taking a measurement here of high frequency ultrasound, right here, you would see a distinct deflection because you're picking up the ultrasound and the dial coming back down. So again, I'll play this again. So you deflect on the meter and then you come back. Deflects on the meter. So the thing is I can walk up to the steam trap and when I'm testing it, I can actually see that operation on the dial or the back part of the ultrasonic indicator. So it gives me that, and also I can hear it discharge and then shut back off. The other one is a continuous flow type steam trap. Now the continuous flow is always passing condensate, but there'll be some cycling to it. There you go, here. And just watch the indicator here. You see the cycling here. So when you're testing the steam trap here, you see some cycling on your indicator of your ultrasonic unit. That's exactly what we want to see. That tells us correct performance. Now, high frequency testing, we want to say that we should be somewhere around 6 to 10 inches here for our first reading, and that's a estimated distance. We can come up and take more readings upstream if we want to. The same thing downstream, 6 to 10 inches, but we can take more readings downstream. We want at least 2 base points for testing the steam traps. Now, here's an example test results that we did. So up here on the first test point here, we had 32 dB. Okay, down here stream we had 34 dB. And right here at the discharge of the condensate orifice in the steam trap, we had 34. So if the ultrasonic sound is equal to or less than 0.1 or 0.2, the steam trap is good. So equal or less, the steam trap is good. If it's equal or less, our base point. So this steam trap proved to be working good. Now, proper operation here, when this steam trap discharges, here, this reading here is 34 dB. It discharges, as you can see, it's going to discharge. The reading will go up and then come back down. So this reading is high, it's in discharge mode. Just wait for the steam trap to finish discharging and then come back to your base point readings. If it doesn't come back, it's leaking or blowing. But cycling steam traps, you might catch it when it's in its cycling mode, so we have to compensate for that. Now, here's a steam trap that's completely failed, and you say, well, how do you know it's completely failed? Upstream reading a 25 dB, downstream 32 dB, and here we have 64 dB. So, has to be equal or less than these two readings, and it's not, it's much higher. So, this steam trap is blowing through. So, by just logging in the dB readings upstream and downstream, you can check the accuracy of your field assessor. So when we're doing steam trap station management programs, the sheets come back in and we look at the dB readings versus their test results on their sheets. So it's really a good cross check. Now, the continuous flow type steam traps are floating thermostatics, and we have one additional point that we have to take, and that's the air vent. So I'm upstream and downstream and the condensate discharge orifice, but also I have to test the air vent because there's two orifices or two passages that steam can flow through a floating thermostatic steam trap. So on floating thermostatics, we have 4 test points that we have to take. Our 2 benchmarks or base points, upstream, downstream, but then we want to test the condensate outlet and the air vent. Now, just a comment on this here, the air vent has to be equal or less than T3, the condensate discharge. If it's higher, the air vent is failed. So we want T3 or T4 to be equal or less than T3. So in here, we're going to go through the test results here, okay? Proper operation test point 4, okay, right here, has to be equal or less than 0.3, which I just talked about. Test point 3, when test 4 is higher than test point 3, the air venting mechanism here has failed. So right here, this here is higher than T3, the air vent has failed. So we need to check those 2 points when we're using, this is only on floating thermostatic steam traps. Now, here's a test result here. Oh, excuse me. A little lag here on my computer, but steam trap leaking steam during operation. So I want to see leaking steam. We say if the dB at 0.3 equals 35, we want it to be 5 or 10% higher than test point 2. We consider that to be leaking steam. So if we are here, we're 5 to 10% higher, then we consider it to be leaking steam. Higher than 10%, we consider it to be blow-through steam. So if I was testing the steam trap here, my upstream here would be, let me go back here, up here would be 25, down here would be 32, and my discharge orifice right here would be 35, and we consider that to be leaking steam. As a visual indication, the next is competing ultrasound. We run into this all the time, and you know, I get the review reports done by steam trap companies or steam trap assessment companies, and they say mechanical sound, and I always question it. For one reason is that we take upstream here and downstream here and test for it to, and we hear a clicking sound, is that travel down the pipe here. If there's a check valve sitting down here, a lot of times it's the check valve that's causing the mechanical sound. People use a swing type check valve and they're prone to have high failures. So by going upstream and downstream, high frequency ultrasound is very directional and you will pick it up. So, listening to a steam trap, and the other thing with high frequency ultrasound, listening to a steam trap, you should be aware of some distinct sounds when while testing steam traps. Condensate will crackle, and with condensate flowing through the steam trap orifice, flash occurs in the condensate orifice of the steam trap, kind of mixes and gets you a crackling sound. Steam passing through the orifice is totally a whistling sound, which is a true characteristic of steam passing through the steam trap orifice. So one of the key things is always listen to a steam trap. Until people do it for 2 years. After that, you can watch the meter and take your dB readings. But you can associate the meter readings with the sounds that are occurring into the steam trap. I always watch people and look at their meters. I can tell them exactly what they're hearing in the steam trap. So. The thing is that there's a lot of things go into steam trap testing. One of the things we do have is a SOP that we're more than willing to share with people so they can go out and do steam trap testing very successful. So you can email me or Graham here at our email addresses, and we're more than happy to share information regarding that. The other thing is that if there are any questions on steam or condensate, you can always contact us. This is our focus in life. We do steam system assessments, troubleshooting, we do steam balancing, steam performance. And also a key factor is we do training to ensure any system that we put in will have great operational life and reliable. Long-term impact things we do is we do upgrades, process changes, and improve reliability and safety. The only comment I'll have to you is steam traps operating in pressures under 250 psi should last you at least 10 years, and I would say 15. So anyway, this is my presentation, and if you have any questions, please email me, and I'd be more than happy to discuss anything with you. Or if you have questions, email me. I'm more than happy to answer your questions. Have a great day.